Hello, and welcome to the Balancing Equations, Redox, and Moles video lesson. We're going to begin by talking about balancing chemical equations. Now, for whatever reason, this is a skill that some students have no problem with. They just jump right into the balanced equations without issues, and other students really struggle with this one, and I'm not quite sure what the difference is. We're going to go into a very low level of detail in this video, and if you need more help, if you find you want more help, then I suggest you check out some of the balancing equations videos down lower in this particular module. A balanced chemical equation is simply one where the number of atoms before a reaction and after the reaction remain the same. And so here we have two hydrogen molecules and one oxygen molecule reacting to form two H2O molecules. If we examine this on an atom-to-atom basis, then what we see is we start out with 4 hydrogen atoms and 2 oxygen atoms, and after the reaction we again have 4 oxygen atoms and 2 oxygen atoms. We've bonded them to each other differently, but the number of atoms hasn't changed. And this should be true of any chemical reaction. In any chemical reaction we change our bonding, but we don't change our number of atoms or types of atoms. So tip number one when it comes to balancing chemical equations. Tip number one is that we can only change the coefficients. In other words, these numbers out in front, we can never change the subscripts. And so we have Chemistry Cat over here who has a joke for us. Two men walk into a bar. The first orders some H2O. The second man says, "Sounds good, I'll have some H2O too." H2O2. The second man died. So the joke here is if we change those subscripts, we actually change the chemical reaction. And so our lower reaction right here, we're making entirely different products, not the same reaction. So never, ever, ever change the subscripts, just change the coefficients. Tip number two when it comes to balancing chemical equations. Tip number two is that if we have an element that occurs in multiple products or multiple reactants, we want to balance that element last. And so here we have ethanol reacting with oxygen to produce H2O and CO2. So I like to work typically from left to right. And again, I like to save the chemical that is going to be in multiple reactants or multiple products for last, because that's going to save us a lot of work. And so we start out by balancing our carbons. So we'd end up with, we have 2 carbons on the left, so we need a 2 out in front of our CO2 here to balance it. And then from there we have 6. We have 6 hydrogens on the left side, and so we need to put a 3 coefficient in front of our water to get 6 hydrogens on this side as well. And then we go to balance this thing. We're going to save the oxygens for last. And so if we count up our total number of oxygens on the right side of the equation, we have right here we have 4 in the form of CO2, and then we have 3 more in the form of water for a total of 7 on the right side. And on the left side of the equation, we have 6 oxygens right here, but don't forget the 7th one hiding out here, so we have 7 over there. And so once we've added in our coefficients, these are all balanced. And so a couple tips here. Just note that sometimes you have to work through a couple times before everything ends up matching up. Sometimes if you balance one element, you break another, so you might have to work through a couple times. And the other thing is if you end up with like halves, so let's say we'd ended up hypothetically with like 4.5 O2s, just go ahead and multiply everything through by 2 to get rid of those halves. We're looking for integer values here. And now for my last tip when it comes to balancing chemical equations. We often encounter equations with polyatomic ions. So how do we handle these? Well, the hard way of doing it is trying to count up individual atoms, in this case individual phosphoruses and individual oxygens, but there's a much easier way. Generally, polyatomic ions stay together as a unit during a chemical reaction, so it's easiest just to treat the phosphates in this case as a PO4 unit rather than individual atoms. That's going to save us a lot of work when it comes to balancing. And so that's going to be true again of most polyatomic ions during reactions. Usually they stay together as one unit. So I'd like you to please pause the video now and complete questions 1 through 3 in the worksheet. Welcome back, everybody. Let's talk about redox now. So redox, or reduction oxidation, or oxidation reduction reactions, these are reactions where electrons are transferred. They're actually very, very common. So not all reactions are redox reactions, but many, many reactions are redox reactions. They're quite common in biochemistry, and a very, very simple example of one is the corrosion or the rusting of iron. So iron reacts with oxygen to form iron oxide. And so what happens in this is that one chemical is going to lose electrons, or iron actually in this case, and another chemical is going to gain the electrons. That's going to be our oxygen. And so in this case, it's pretty easy to tell that's what's happening because we go from these neutral elements into this ionic compound. And hopefully you remember from chapter 5 that metals like to form cations, so our iron's now a positive ion in this ionic compound. We know it's ionic because it begins with a metal. And so iron has lost electrons to form the cation, and our oxygen's gained electrons to form an anion. And so again, looking at oxidation and reduction, some people remember this as oil rig, and so oil stands for oxidation is loss of electrons. So in this case, we have a zinc atom that's going to lose electrons to form a zinc ion, and now we see that there's also electrons in our product side here. So this is being oxidized, it's losing electrons. And then rig, reduction is gain of electrons. We have here a copper ion that's going to gain 2 electrons to become a copper atom. And so for reactions that involve ions, we can simply look at our changes in charge. If something becomes more positive during the reaction, that means it is losing electrons, it's being oxidized. If something becomes less positive or more negative during a reaction, that means it's gaining electrons, it's being reduced. When it comes to reactions of covalent compounds, our rules are slightly different because we don't have the same type of charges we see with ions. And so how we identify oxidation in reactions involving covalent compounds, and this also relates to biochemistry, is we're going to see a loss of hydrogen and or a gain of oxygen. And reduction's quite the opposite. So for reduction, we're going to see a gain of hydrogen and or a loss of oxygen. So here's an example. This is nitrous oxide combusting with octane to form CO2, water, and nitrogen. So let's take a look at our nitrous oxide here, or N2O. And so our nitrogen is actually losing oxygen during this reaction. So if we're losing oxygen, that means our N2O is being reduced during the reaction. And then if we look at our octane over here, we notice that our carbon is actually losing hydrogen and gaining oxygen as it forms our product here. So our octane is being oxidized. So in any redox reaction, one of your reactants will be reduced and one of your reactants will always be oxidized. Those two things have to go together because if something's losing electrons, something else has to be gaining them. They don't just magically disappear or something like that. All right, so this is where it gets confusing. Our reactant that's oxidized during the reaction is actually referred to sometimes as a reducing agent. Now this might seem totally confusing, and it is confusing, but let's talk about how it sort of makes sense. Well, if we have a chemical that's being oxidized, that means it's losing electrons. That means it's giving away electrons to another chemical. And so it's helping to reduce our other reactant by giving electrons to it. And sort of conversely here, our reactant that's reduced during the reaction is referred to as the oxidizing agent. So if it's being reduced, it's gaining electrons. It has to get them from somewhere. So whatever chemical, it's essentially stealing those electrons from another chemical. We call that the oxidizing agent because it's helping to oxidize our other reactant. I know it's confusing, even for chemists, but stick with it. You'll get the hang of it. So please pause the video and take a shot at questions 4 through 6. Welcome back. Let's talk about our final topic, which is the topic of moles. And so moles are a certain number of particles. So moles for elements are going to be 6.02 times 10 to the 23rd atoms. And so if we look right here, a mole is going to again contain 6.02 times 10 to the 23rd atoms, regardless of what type of element we have. It's kind of like the term a dozen. It doesn't matter what we're talking about. A dozen means that we have 12 of something. A mole means that we have 6.02 times 10 to the 23rd of something. And similarly, if we have a compound, then we would have, for instance, CO2. A mole of CO2 would be 6.02 times 10 to the 23rd CO2 molecules. And you guys are probably seeing where this is going. Regardless of what type of thing we have, a mole means 6.02 times 10 to the 23rd units of that thing. Now this seems like kind of a crazy number. Why would someone pick 6.02 times 10 to the 23rd? Well, there's a clever trick behind it. We've talked about these quantities below the periodic tables before as being the average mass of an atom. So an average carbon atom has a mass of 12.01 atomic mass units. But this number actually has a second meaning. It means the mass of a mole of carbon atoms in grams. So this, again, is the mass of a single atom in AMUs, or the mass of a mole of atoms in grams. So that's why they picked that weird number. It allows this atomic mass in the periodic table to essentially have two different meanings. So how do we find the mass of moles of compounds? Well, it's actually pretty simple. We just sum together the elements that are contained inside of them. So if we try and figure out the molar mass of calcium chloride, a mole of calcium atoms has a mass of 40.1 grams. So we get that just straight off the periodic table. And the mass of 2 moles of chlorine atoms is going to be 71.0 grams. That's 2 times our molar mass of the chlorine, because we have 2 chlorines here. And so we sum together the mass of our calciums and both our chlorines. We end up with 111.1 grams being the mass of a mole of calcium chloride. And we can use these quantities to convert between moles and grams and moles. That's going to be a skill we're going to be using throughout the remainder of the quarter. So how many moles are present in 65.1 grams of potassium chloride? Well, we have to sum together the mass of the potassium and the chloride, and we come up with 74.6 grams for every mole. We can set up whatever these two different ratios right here from that quantity. But we're going to set up our unit cancellation now. Yep, unit cancellation's back. So we're going to have 65.1 grams of KCl, and that's going to be for every 1 mole, 74.6 grams. Notice our unit cancellation. And we end up with 0.837, or 0.873, excuse me, moles of potassium chloride. And so here's another example. We're going in the reverse direction now. If calcium carbonate, we have 0.320 moles of calcium carbonate, how many grams are present in this sample? Well, we're going to use our molar mass. We sum together the mass of a calcium, a carbon, and 3 oxygens. We end up with 100.1 grams for every mole. 0.320 moles, and then we now have our grams on top, our moles on the bottom, so they cancel with the moles over here, and we end up with 32.0 grams of calcium carbonate being present in that sample. So I'd like you to now pause the video. Please attempt to complete questions 7 through 9 in the activity, and I suggest you post in the discussion section of Canvas with comments, tips, questions, things like that. All right. Thank you. Bye.